you very much. Let me just get my slides shared for everyone here. And then let me see, I like to kind of arrange things so I can see comments in the chat a little bit. So let me pull that up in case people want to. Please do ask questions. Yeah, let me get started here. So thank you very much for having me to chat with you all virtually this morning. And I'm going to be focusing on gravitational wave observations today and how they tell us information about dense matter. So sometimes when I'm talking about dense matter, for some of you, this will be an area you're very familiar with. So please bear with me as I reintroduce it to you. And do let me know if there's any misconceptions that have crept into my understanding of the more nuclear physics side of this. But most of my talk, I'll be focusing on the gravitational wave side. So just introducing how LIGO and Virgo have observed in particular two neutron star mergers that tell us some information about the kinds of neutron stars that exist in the universe and what their interior properties are. I'll talk a little bit about how those dense matter properties are imprinted on a gravitational wave signal, and then what the observations of the gravitational wave data have constrained the dense matter properties, and a little bit about where we'll be going in coming decades. So what are the prospects of this field for what it will be able to help understandings of dense matter physics. Okay, so just to orient everyone, since we're talking about distant sources, the imprint on gravity, the imprint of gravity is typically felt as a tidal field rather than the direct pull that we're most familiar with here on Earth. So for example, the impact of the moon on Earth is felt through the tides, and the gravitational waves, there's a nice little website that I've linked here. You can't follow the link right now, but I'll probably share my slides or something later, that goes through how you understand gravitational waves as oscillations in the gravity gradient that changes, stretches, and squeezes distant objects, similar to the way the tidal field stretches and squeezes the Earth, most noticeable in the freely responding water. So as soon as we put matter into motion and we realize that we're dealing with a relativistic theory of gravity rather than one that has instantaneous action at a distance, you end up with gravitational waves. So the gravitational effects carried by the curvature of space-time, as that curvature changes, the change must propagate, and it will do so at the speed of light in general relativity. If you linearize the equations of general relativity, you get a wave equation. And the effect of the waves is going to be to stretch and squeeze the distance between this ring, this red ring of freely falling objects. And that oscillation pattern carries itself through space with the standard wave properties of two polarizations of these oscillatory stretches and squeezes that have real physical effects on distant particles. Of course, the effects are quite small. So if I talk about the change in length that two freely falling particles would feel as a ratio with their distance between them, this is the strain that a gravitational wave observatory measures. We find that with some constants, this will be proportional to the mass that's moving, the velocity that's in the perpendicular plane to your line of sight. So direct forward and back motion wouldn't change the long-range gravitational effect you would feel, but side-to-side type motion would. So that's what conveys gravitational wave. That's what generates a gravitational wave. Then 1 over the distance r to the distant sources. And if you put this in with some astrophysically relevant numbers, so 100 megaparsecs is sort of a reasonable distance you might expect to see something at. We got one at 40, which was pretty lucky the first time for neutron stars. The mass of a neutron star here. The ratio of the separation between the two objects to the Schwarzschild radius. Schwarzschild radius is the radius of a black hole of the same mass. And you get something that's minus 10 to the 21, which is the scale of change that the LIGO Observatory was built to observe. So using gravitation or using laser interferometry, plus a bunch of quantum tricks and optical cavities and isolation systems and such like to measure relative length changes on the order of 10 to the minus 21. So as we observe these length changes, they map onto the dynamics of the source system. So the frequency of the source system is related to the frequency of the oscillation, the orientation of the source system, the distance and masses of the source system relate to the amplitude of the oscillation we see. And so the name of the game then is going to be trying to translate from the oscillation pattern you see what source is going to generate this effect. And we have, I guess, a driver of transient signals here, which is the loss of gravitational wave radiation itself, which is a huge amount of energy loss. If you, again, do these sort of scaling relationships to how the gravitational wave depends on the compactness, the mass and the separation of the two systems of the source system to the 5th power, you get something like 10 to the 59 ergs per second, where I'm using the kind of units astronomy folks like to use. Again, with the Schwarzschild radius of the mass involved to collapse to a black hole related to the length scale of its motion. So then this energy loss means that the separation between the two orbiting objects will decrease. That in turn has a positive feedback loop, which increases the gravitational wave luminosity. And we get these characteristic chirp patterns that we're going to interpret, where the change in the frequency, the change in the orbital separation as you go along, is characteristic of the energy loss that's happening. So we measure the energy lost as two orbiting bodies interact with each other. So that's going to be key in interpreting the observations of gravitational wave signals. So with the gravitational wave observatories we have today, we have the LIGOs in the United States, Virgo. GEO is a detector in Germany, and Kagra in Japan, which have also been taking astrophysical data. And then there's a LIGO clone, so to speak, in India that's under construction, which will improve the localization, the ability to triangulate sources in the sky in future observing periods. So I won't go much at all into the details of the experimental design, the monitoring systems, the suspensions that isolate them from environmental oscillations of the Earth. But these are, large-scale facilities. These are parking lots and cars across the globe that are now measuring gravitational waves. So far, in the time that the detectors have taken astrophysical data, we have now 67 strong candidate gravitational waves that were immediately released with all the information we had at a short period of time, which have in the last O3A and O3B, the last observing runs included new candidate classifications like neutron-star black holes to go along with the black holes announced in O1 and double neutron stars announced in O2. So we have a gravitational wave population now where, if you look at, these are numerical simulations of fully relativistic black holes with their horizons marked in blue. And depending on the masses involved, you get, and the distances, you get different characteristic in-spiral chirp patterns, which here have been used to match the best fit data to a numerical simulation that's compatible with the parameters that fit the signal in the data. So we start to see a population of a range of black holes, and with masses that range from sort of 5 solar mass scale to, oh shoot, I think there's another one that I haven't updated. This was from May, and there's the very large neutrons, or very large massive black hole announcement, which I won't talk about, but it's really cool actually for nuclear physics because of stellar populations and the nuclear physics of progenitors of massive black holes. But I'm going to focus here on the low mass side of things, which also has some intriguing mystery objects in it. But for some amount of time focus, although I'm happy to talk a little more about other signals if folks have particular questions after, I'm going to be focusing on the double neutron star mergers here today. So. Okay, are there any questions here so far? Okay, then let me continue. So I showed numerical simulations of black hole mergers. We also have numerical simulations compatible with all the data we've observed for, say, the neutron star mergers. So this is an example simulation for 1708-17 and the final 40 milliseconds. So a lot of it is a little more boring than this. As the stars get close, you start to see their surfaces deforming from the tidal tugs between the two objects. They merge off the exciting material to generate the kilonova observed in the optical afterwards. Probably lived for a period of time in milliseconds, oscillating a little bit above the sensitive frequency of our detector, then collapsed to a black hole with some disk of material around it that would have then generated the associated gamma ray burst that was observed. We also had a second signal, and again, if you look at the final stages of this observation of this signal in association with parameters that are compatible with our knowledge of both the properties of the system and equations of state for the neutron star matter that match the previous signal. We see that these are more massive objects. They still deform each other, but not as strongly. And most likely, from our understanding of the parameters, they would have collapsed to a black hole upon their merger, with very little release of material into the interstellar environment to generate any associated electromagnetic counterpart. Which we did not, which was searched for this signal, but was nothing significant was found. So one of the interesting things that comes out of looking at the dynamics of these systems is that the mass scales involved in the two is pretty different. So 1708-17, the first neutron star merger, was pretty much smack dab in the middle of a population of galactic double neutron star binaries that had been observed previously. But the second signal that LIGO observed, 1904-25, was notably different, more massive than these galactic double neutron stars, which changes a little bit the assumptions you want to make when you analyze the data. But one thing you can note is that there are examples in our galaxy of massive pulsars, so massive neutron stars like Vela X1, which have a companion which could potentially itself eventually become a neutron star. So it's not that this is something impossible to conceive, even based on our own observations in our own galaxy. So we're just seeing probably many different selection effects here coming into play with this comparison of the gravitational wave sources and the electromagnetic observations in our galaxy. Okay, so how are we going to use the dynamics of these binary orbits traced through from gravitational waves to learn about dense matter, and what kind of dense matter do we actually talk about when we observe gravitational waves? So, as an overview slide, what are sort of the thermodynamic properties of merging neutron stars that are relevant here? And so first off, when you have the neutron stars separated and inspiraling, these are stars that have cooled over their long, slow inspiral before they reach the frequencies relevant to LIGO detectors. So they're going to be cold, negligible for the purposes of understanding matter effects. And when we see them in inspiral, we're then measuring the density above nuclear density in the sort of characteristic density of these stars, which will vary as they get more massive, but negligible temperature. Once they collide, we can call that the post-merger regime. We have an interesting phase where the central densities and the temperatures increase on rapid timescales. And then we observe outflung matter that originated at these high temperatures and densities, but is rapidly returning, cooling to nuclei, which is the kilonova powering the nucleosynthesis, the chemical nucleosynthesis of the the heavy elements that we observe here on Earth, or at least some portion thereof. So the relevant kind of terrestrial information we have to play into our understanding of this kind of density regime would be both the neutron matter at densities such as say a neutron star skin thickness measurement below the density of below nuclear density. And then we also have maybe more from something like heavy ion collisions, symmetric neutrons, oh my goodness, symmetric nuclear matter, where you have equal numbers of protons and neutrons roughly, and giving you relationships between pressure and density in these two phases. And so this is sort of one theoretical test of our frameworks for understanding dense matter. For neutron star matter, we need to take primarily neutron matter above nuclear density. Of course, you would probably expect other degrees of freedom to start to play a role, like hyperons or something like that. But you have, again, a wide range of theoretical possibilities compatible with the data so far. So if I look at a paper from 2017, for neutron star relevant equations of state, you have some equations of state that are just nucleons, some equations of state with additional degrees of freedom, and they can be mapped onto the radius. So higher density pushes out the matter more, larger radius. You get a range of radii that goes from maybe 12 to 15 for each, or lower for additional degrees of freedom. They need to match the heaviest neutron stars observed in our galaxy, which are around 2 solar masses. So that's a challenge for, say, any of these guys down here. And then now I'm going to show how gravitational wave observations additionally favor radii that are dense, or radii that are smaller, pressures that are lower, which becomes challenging for these scenarios with additional degrees of freedom, and while still retaining the ability to produce 2 solar mass stars. So this is getting to be a constraining set of observations on nuclear physics. As the stars merge, here's a comparison from Hanasuke et al. Comparing the relevant temperature and pressure and densities from the collision, when you start on the blue end here, from the most dense to the, I think, outer reaches of the star. So we have a spread of densities within the star as they merge, and then in the post-merger, the central densities increase. The temperatures also do some exciting stuff, but typically at lower, or around nuclear density rather than up to 5 times nuclear density. And then this is comparing to gold ion collisions at high energies. So we're starting to see some crossover, I guess, in the terrestrial and extraterrestrial laboratories of nuclear physics here. Okay, so how are we going to get information about this matter from the gravitational wave itself? So I'm going to be focusing onto the period before merger, basically before the stars smush into each other. So that's what's happening here. That's roughly where the peak instantaneous gravitational wave amplitude is. For most of the orbit, so this is only a small fraction of a second in the final stages, the 2 stars orbit each other with some small tidal deformation, which we can measure. And then as they approach each other, things get more complicated. But we have ways now to handle that modeling that I'm going to briefly overview here today. Okay, so the leading order effect, and really what drives our measurement, is a Newtonian tide mapped into the relativistic system. So we actually define this parameter from a cold equilibrium star, and then we test and we use it in our models and test that this is a effective parameter with more complicated simulations and analyses. So basically we have something that's the ratio of a quadrupole deformation and an external tide that's inducing that quadrupole deformation. The dimensionless form here is the one we use in our gravitational wave analysis. And the key idea is this is very closely related to the radius of the star divided by the mass of the star, or the compactness, with a high power. So this really drives what we measure when we measure the gravitational wave parameter. So the compactness of the star plus another relativistic love number. The love numbers were developed for Newtonian physics, and they have relativistic analogs developed by De Moore in the 80s. They have some range that influences the magnitude of this number, and they're going to characterize how the mass is distributed within the radius that dominates this tidal signature. So a larger star with a higher radius, higher pressure in the matter inside, will be more deformable here, just because a more compact star, I guess, maybe is easier to think about. As it gets more compact, it's harder to squish the matter around. The gravitational pull on the nearby matter to its own core is more difficult to overcome. So just as the equation of state gave you a range of radii, it will also give you a range of this tidal strength parameter that is larger for large radius equations of state, smaller for small radius equations of state. and then we can, within the bounds of the masses produced by our gravitational wave data, we will see which of these values is preferred. The way that this impacts the orbital dynamics traced in the gravitational wave signal is primarily that additional orbital energy is lost along with its loss to gravitational waves. It's also lost to deforming the stars. And the tidal bulges also add a little extra quadrupole gravitational radiating power, but the driver is really this orbital energy lost. So where we started with the change in the radius, sorry, I'm flipping around my notation a lot here, but hopefully this is just a problem because there's too many radii involved in these things. The radius change over time from the ratio of the gravitational wave luminosity to the change in energy with the separation of the stars. We add a little change in energy from the deformation. We add a little luminosity from the bulges, and we get something that started out as a simple chirp, has a merger, a high amplitude part that is earlier. There's here, this is only showing the final stages, but there's a trace, a small trace that's affected the initial conditions. I think these two, this waveform pattern was started generating at 100 hertz. So there's some small change that really becomes most significant in the final orbits of the stars. And then of course there's some sort of Kirby dragons for what actually happens after the stars collide. Okay. I'll pause here in case folks have questions. I don't see any though, so I'll continue and hope that folks will follow up with me after the talk. So the upshot of all this, so what is the actual theoretical modeling we rely on to extract information from our signals? We're going to describe waveforms up to merger. So far and for the near future, we expect the information we extract to be before the stars collide. So this is cold equation of state information. The waveforms are characterized by the masses and the spins of the two objects and the component lambdas. And actually, the component lambda is primarily in a particular combination that is the leading order combination in the gravitational wave dynamics. And then we'll use this to modify our template waveforms that we use to compare to the data in one of two ways. So one way is to take black hole models, binary black hole models, which are well tested with simulations and observations of binary black holes. And we just add that leading order tidal phasing in, plus some phenomenological higher order terms that we pull out of the numerical relativity simulations. And then the leading order is really the driver, and the variations between models will come primarily from these phenomenological higher order terms. Although they can also, well, I'll show you some results actually to go through that. And then the other technique we have is to directly generate semi-analytic models of the dynamics of neutron stars merging with what are called effective one-body gravitational interactions, analytic tides, including higher order terms, mathematical techniques like resummation to try and cope with the fact that these series are not, perturbative series are not really behaving themselves properly. There's dynamical oscillations of the stars that can be accounted for analytically. They're kind of in the numerical relativity because that can do whatever movement of matter at once, but for the semi-analytic models, you need to put in tides and resonances by hand. So we have various ways to do that we'll compare when analyzing the data. So a gravitational wave signal like 170817, the pieces of this description that gravitational wave astronomers end up staring at are going to be this combined tidal parameter. This is just the coefficient on the leading order term. We call it lambda tilde. Q is the mass ratio, and the smaller mass divided by the bigger mass. Chi is an effective spin parameter, similarly kind of trying to get the leading order behavior. And it turns out that along with the underlying chirp mass, the sort of equivalent of total mass, but the one that really drives at leading order the gravitational wave dynamics, these are the things that we actually pull out of the signal. This is the framework we use to understand it for signals so far. So this is where we see, for example, that spin and mass ratio are highly correlated, and tidal parameters are a little bit correlated with those two things too. We generally will, so for example, if we assume things about the spin, we can limit our resulting inferences about the mass ratio. And also that changes a little bit the tides. Spin can look a little bit like tides in the way that it accelerates the merger of two objects. So the best way we can kind of look at this for 1708-17, we have these different ways to model the system. Binary black hole variance with numerical relativity calibrated tides, or ground up semi-analytic models, or what we started out with in 2017, we only had initially perturbative models that we just ad hoc tried to match to some of the best state-of-the-art other versions we had at the time. And then the result then has some systematic uncertainty in the bounds of, say, this tidal parameter that come from these different modeling frameworks. One thing to note, though, is that this is this is sort of an open analysis where we make as few assumptions as possible about what the system looks like. For 1708-17, based on comparison with galactic binaries, you would perhaps say the spin is probably low. And it turns out the differences between the models come a lot out of the spin sector. In the way that semi-analytic models can differ from these binary black holes within our tides models. And so there's significantly more consistency between our state-of-the-art models. Ignore perturbative, does not use all available information. But we have a broad consistency here for the analyses across these different frameworks for modeling the system. For 1904-25, the second neutron-star merger observed, we say we have something like an uninteresting upper bound. So roughly the posterior distribution for our lambda tilde parameter is flat over the range of values you would predict for it if you used information from previous observations and this observation's masses. So this distant was more distant signal, less amplitude, and also with smaller tidal effects because of there's the 1 over to m to the 5 factor with the mass of the body. Just means this is both harder to measure and it was a fainter signal. So we really don't learn anything new relevant to tides specifically from this signal. We can take these lambda observations and map them into radius constraints, either through the equations of state or some relationships that broadly hold that relate radius and lambda parameters for many equations of state. So that's equation of state representations with models for the equation of state or phenomenological relations between them, between tides and radii. And we get broad agreement now that the radius of, say, a 1.4 solar mass neutron star, these are all for the same system. So these are separated in mass, not because they're different mass systems. All these are for systems roughly around 1.3 or 5 or 1.4 solar masses. But we're getting overall consistency in our understanding of the mass of neutron stars. You can then translate this directly into equations of state, pressure density relationships within the stars. So here's sort of an example how, as you go through and add more data to a generalized functional representation of this relationship, heavy pulsars get you to this first teal curve, which means it has to get high pressure enough to support those massive stars. Gravitational waves push you down here in the sort of 1 to 2, a little bit of 1 to 2 times the density of a nucleus regime. If it's too much pressure here, it would have had a stronger effect on the gravitational wave signal than we saw. And then we also have X-ray observations that support more large radius stars. And that sort of tightens you up again from the bottom end, and you have this sort of now joint constraint that's starting to trace out almost, well, that start to trace out a meaningful range of pressures at each density compatible with all astrophysical information currently available. We can start to do things like say, like if there is a phase transition, if there are two stable branches of stars, where must it happen? So if there are two stable branches from these observations, we would see a structure of equation of state that had this dotted green shape compared to the most often you don't see this structure in your randomly generated equation of state functions. So that's just the difference if you assume that some strong phase transition has happened. And there's some alternative ways to do each of these steps that are referred to here. So this is results from Phil Landry, Read Essick, and Katerina Tatsianu in 2020, but there's a similar LIGO Virgo version with a different framework for describing the equation of state, has similar results. There's other ways to consider strong phase transitions, and one cool result coming out of this joint analysis of astrophysical observations is that the speed of sound within the neutron stars, well, it's not entirely possible that it has to exceed a third. It's looking more and more likely that it should at some point within the density ranges of neutron stars. So if you're looking for it eventually for ultraviolet, for quark matter to come to that speed of sound, a third the speed of, I'm losing my squares. Anyway, so there's interesting results about a potential structure in the speed of sound of dense matter as a function of density. This is compatible with X-ray constraints from, say, 2000 and from pre-LIGO era that also tended to favor massive stars. So there's Ozell and Freyre, Steiner, Latimer, Brown, and the LIGO Virgo collaboration, which at the very least has completely different systematic uncertainties, now is starting to build a consistent picture with these. And then as we've seen, those astrophysical X-ray constraints and now the LIGO Virgo gravitational wave constraints can be compared to terrestrial laboratory results to learn about, say, the difference between symmetric and anti-symmetric dense matter, or to just to compare. You could actually use this to test general relativity if you want to, because the astrophysical analyses here assume that general relativity is the correct theory. So the fact that these are compatible means that, well, not surprisingly, it's doing a reasonably good job. I actually said that already. Apologies. Okay. So what's next? So let me just close here in the last few minutes by saying a little bit about where we go from here. So currently, the LIGO Virgo Kagra, Kagra is the Japanese detector, the plan is well under development. We're aiming to continue improving sensitivity of our ground-based detectors in the coming, say, 5 years or so, down to this pink curve where I have noise as a function of frequency, so lower noise is better. This will improve the neutron star range by a factor of 2, so the rate by maybe a factor of 8. High frequency sensitivity, which is where the data we use to constrain equation of state primarily lies as the neutron stars approach each other. That will be better sensitivity by a factor of about a 4. So given the same signal at the same distance or strength, we would get very hand wavy, roughly 4 times better limits on, say, tidal parameters. And we have a rate here that's compatible with actually predictions that were made back in 2010, that it would be roughly 1,000 gigaparsecs cubed per year. Well, it's between, I think as of the latest result, between 250 and 3,000. So, you know, on astrophysical rate scales, this is a really good setup, and that's compatible with 40 per year detected when we get to design sensitivity of 0.5. So this, in combination with something like NICER, would continue to throttle in on the range of equations of state that are compatible with the data. Although 1708-17 kind of out punched the observatory class at the time. It was so close and so loud. We really lucked out to be able to make strongish constraints with the very first signal. You know, these things really depend on what the universe gives us, but the idea is that we'll have some improvement from, you know, roughly where we are in the teal bands to after 04 and 05, we'll start to kind of narrow in, particularly in this twice nuclear density regime. Of course, you know, no field of physics is content by just building a detector and then turning away and saying, well, that was fun, let's do something else. We want to see more gravitational waves. There's a whole spectrum from the audio frequencies of advanced LIGO that I've been focusing on here. Well, there's ways with Cosmic Explorer and Einstein Telescope that I'll talk a little bit about here. To get better sensitivity there. We're also going to be looking for lower frequency signals. That lower frequency is larger mass with the gravitational scaling. So this would be something like massive in-spirals, white dwarf binaries in our galaxy, and then supermassive binaries with pulsar timing arrays that are feasible with future radio pulsar observation prospects. So we would potentially then be able to see binaries of all masses and out to significant redshifts on sort of cosmological scales. And also for the nearby sources with these next generation observatories like Einstein Telescope, Cosmic Explorer, and LISA, we'll getting signal to noise ratios into the thousands or so. So we have an unprecedented fidelity, which would have a big impact on the way we can measure information about these parameters. So here on the ground, we're currently at the sensitivity of advanced LIGO. We're moving to Advanced LIGO Plus. This is, I think, what's currently planned out over the coming years. Voyager is roughly the limits of the current facilities. So with improvements in the technology installed with the current kind of scale of gravitational wave observatories, we could make improvements down to this orange curve. Then to get say an order of magnitude better than that, we need to build new observatories, larger scale facilities And the proposals that are being considered primarily for those are called Cosmic Explorer or Einstein Telescope. This NEMO is an Australian proposal that would focus on the high frequency. And so all of these are all of these below LIGO A+ would be something that you would maybe expect to see in the 2030s or hope to see in the 2030s. As we go to more sensitivity, so right now we are in this sort of initial 03 light blue band where we see only our immediate neighborhood of gravitational wave sources. So, you know, small redshift, even for the black holes, which we can see further. But as we improve sensitivity, the goal of, say, the Cosmic Explorer design is to see, basically, as we understand it today, all the emerging neutron stars in the universe out to redshift 10. Probably there aren't any before then. If there are, that would be really cool. We would see black hole mergers resulting from any stellar evolution before the known before the current populations of stars. So longer term, what this would mean for our, say, uncertainties on tidal parameters would be, you know, here was how well we did for 18, 017, and 02. If we measured that today, we would do notably better because of improvements in high frequency sensitivity. As we go forward into more and more facilities, we really start to break our modeling assumptions, but the fidelity would be potentially exquisite for something like 170817 happening again today or in the future. The population, so here's the universe of neutron star mergers out to redshift 10. Cosmic Explorer detects neutron star mergers, most of them. Potentially, the limitations become not the signal-to-noise ratio of an individual signal, but the data processing required to extract overlapping signals reliably from a large population of, you know, thousands of signals per month. You know, right here, we're in the nearby universe with, you know, for 8+, the design feature, the 40 per year stage, we would have maybe a few per month. So that's all I had to talk about today. If you're interested in Cosmic Explorer, there's a way there to sign up for a consortium to get on a mailing list and contribute to our science ideas. LIGO and Virgo, we release open data so you can play with it yourself, and there's some Python notebooks and tutorials there that can let you can analyze the signal your own way and interpret it with your own preferred models for neutron star matter. And fun fact, Cosmic Explorer arm would be roughly the distance across of emerging neutron star. So I'll stop now and ask for questions.
Thank you very much for the nice and clear talk. So are there any questions? Please just unmute or raise your hand.
Yeah, I have a question. So I may be making up, it may be a silly question, but I heard that some groups are worried about the effect of dark matter has on the neutron star merger. Can you roughly, did you have idea about by how much will your equation of state change if the assumption of dark matter is added into neutron stars?
Yeah, so this is this depends on the model of dark matter you're using and also how much dark matter you assume that has accumulated. So people are right now looking at 170817 and reanalyzing it with dark matter augmenting the system. So let's see, what you do end up basically with a degeneracy between the amount and kind of dark matter and the exact equation of state of neutron star matter. So a gravitational wave signal with dark matter would look effectively like a like a neutron star that had a different radius and mass. So the challenge then is, instead of the pure nuclear matter relationship between mass and radius, you would have a tidal dependence on mass that had a different behavior. If you have too much dark matter, it can just like collapse stars earlier. Anyway, so so I guess what you could say is these constraints. For example, if you're like, I do not believe neutron stars are that compact, no way, no how, then you can just put in a bunch of dark matter and get the and then the effect on the gravitational wave signal is that the star is effective compact and it doesn't deform. And so that would be, say, a way to have pure nuclear matter stars that had large radii and still astrophysical observations that have small radii.
Thank you.
Yeah. Justin has his hand up.
Yeah, so I had a quick question on your plots of lambda. They tend to show some kind of like bimodal behavior.
Oh, sorry, let me just share that again.
Okay. So yeah, I was just wondering if there's an explanation for why lambda in the probability distribution function tends to be bimodal, and if there's any significance to that, and if that tells us anything physical about anything.
So it's not necessarily anything hugely significant. So you can get this kind of structure if you just analyze injected signals in artificially generated noise. I think that it has something to do with as the tides get stronger and you accelerate the final stages more, you can kind of go in and out of phase between your model and the data and get multiple peaks of overlap, if that makes some sense. But you'll notice that it's specific to this one class of in our tides models that pick this up here. And then if you're worried about 1904-25, the double peak here is from 1708-17. So that's the same double peak structure. The new data doesn't really show that same effect. But yeah, so this, as far as we can say, this is just a thing that randomly happens sometimes, and it doesn't have any deep meaning.
Okay.
But, yeah.
All right, thanks.
So Jocelyn, this is Dean Lee. I couldn't raise my hand because I'm one of the co-hosts, I guess. But
oh yeah, sorry.
But my question is, can you say something about the alignment of the neutron star spins with the orbital angular momentum, and what happens if they're not aligned, and how does the dynamics evolve?
Yeah. So pragmatically, maybe, when you observe the effects of spin on a system, this effective chi parameter comes from the components of the spin that are aligned with the orbital angular momentum axis. Mm-hmm. So that's what drives most of the dynamic behavior of the system. And then if you had, the stars like spinning rapidly, but mm-hmm. like in plane, then their chi effective would actually be 0. So there are more parameters than I'm showing here, and there are subtle effects to disentangle scenarios where you have them. One thing I can say is that really there should be absolute value bars on this assumption of low spin, and then typically we marginalize over the direction of the spin uniformly, but you could reanalyze it with different spin assumptions. For the black hole game, people have done a lot more looking into what are the right assumptions about spin to make for the kind of astrophysical statement you're looking into. But so far for neutron star tides, because the driver of the correlations with the tidal sector, so to speak, is this effective spin parameter, which was a line spin, that's mostly what we focus on understanding.
Thank you.
Okay, Betty is next.
Yeah, hi. So I have a question about the neutron star mass distribution. So before LIGO, so there, just from astrophysics point of view, the distribution is more like peaking around 1.4, maximum around 2.1, something like that, 2. So right now with the LIGO observation, you build up a distributions of masses, even though you may not have as much physics as you want. Do you, does that agree with what was observed astronomically? I know for sure, for example, your 190425 is much bigger than the others, right?
Right.
So how is the distribution different in the two, from the astrophysical observation and from LIGO?
Yeah, so I'm right now trying to find something about mass distributions to share with everyone.
Yeah, by the way, I'd like to compliment you. That's a very nice talk. I enjoyed it.
Thank you. Okay, so if okay. So yeah, so one of the things you need to worry about if you're talking about mass distributions is selection effects. So gravitational waves, massive systems are louder. So if there was a uniform distribution in the overall mass scale, you'd get more heavy signals than light signals. That favors these more massive systems for gravitational wave observations compared to the standard, say 1.36, 1.36 mass system of 1708-17. So there is sort of a fundamental better chance of observing more massive stuff from the nature of gravitational wave observations. Now, another thing that we have is that galactic neutron stars, well, the double neutron stars really live in this 1.35, 1.35 regime. There is, I hinted at this with the Vela pulsar, a populations of more massive neutron stars that have been observed, just typically not in binaries with other neutron stars. So you can, envision a scenario where advanced LIGO observes a joint population of mostly massive or mostly low mass neutron stars at around 1.35, 1.35, like 1708-17, but it's not so infrequent that you get this secondary sorting of 1.8 and 1.35 systems like, say, 1904-25. So the background distribution here, this is actually an undergraduate student here at Fullerton put this together. So the background distribution is coming from a electromagnetic observation generated population. So that's just taking this 2017 mass distribution from the galactic population, randomly assorting them together, putting in the LIGO selection effect, and getting this underlying distribution of the two components. The lower mass star tends to be one of these 1.4 guys, but the higher mass star actually has as good a chance of anything to be a more massive neutron star. So we have this sort of, there's lots of more population dynamics to go into it, but yeah, so it's not, it doesn't take too much hindsight to make 1904-25 compatible with 1708 or with the galactic observations, but it is something that hasn't been observed directly.
Okay, thank you.
Okay, I see no more questions. So thank you again for the talk. I really enjoyed it. And yeah, I would like to close the session.